Hi everyone. Today I want to start chapter 14, which is about passive filters. So in this lecture, I'm going to talk about a very major application of the frequency response and frequency domain analysis. So when we are talking about passive filter, we want to do some frequency domain analysis. This application, which I'm going to talk about in frequency domain, is called filters. Filters are incredibly useful. They are used in virtually every electronic device in some form or another. For example, every single cell phone has a set of filters. So let's start with a review, and then we are going to focus on different type of filter and how they act in front of different frequencies. You should remember that in our previous chapter, we talked about steady state response of a circuit or a system. So here is a review. We had a system or circuit, and we know the transfer function that describe this particular circuit. This transfer function basically tells us what is the relationship between the Laplace transform of our output and input. So it tells us what is the ratio of y of s over x of s. Now, in a steady state analysis to AC input, or in another word, to sinusoidal input, we know that we have two main focus. The first one is that we are looking for the steady state response, and our input is sinusoidal. So if we can assume these two are correct, so we don't care about the transient response and we don't have any other type of input, we only have sinusoidal input. It can have various range of frequency, but it is always sinusoidal. In this scenario, in order to find the steady state response, what we can do is that we can multiply the phasor of input. So this is our input phasor by the complex number that we are going to get by evaluating our h of s at j omega. So h of j omega is going to be a complex number. If I multiply this complex number by x, which is my input phasor, I'm going to have another complex number, and that complex number in polar form is going to be the output phasor. So it tells me what is my output, and I can easily describe my output in time domain by applying a phasor inverse transform. So let's show this in an example. So I'm assuming that I have a transfer function, and in this transfer function, h of s is equal to minus 10 to 4 multiplied by s over s plus 400 multiplied by s plus 1000. So I know what is the transfer function of the system, and I'm assuming that I'm applying an input which is equal to 2 cosine of 400t in time domain. So it means that its phasor is equal to 2 with an angle of 0, and its frequency is 400. Okay, and what I'm looking for is my steady state output. Okay, in order to find the phasor of my output, I need to multiply my input phasor by h at j omega. Okay, let's start with this one. So let's start with h at j omega. This is what I have in as my h of s. So I need to evaluate my h at j omega. Omega is 400. So I'm going to have minus 10 to 4 multiplied by s, which is now j omega, so j 400, divided by j 400 plus 400 multiplied by j 400 plus 1000. Okay, let me cancel out 20 here from 400, cancel out this 400 by the 400 here and here, and then I'm going to cancel out 2 zeros by these 2 zeros and these 2. So I'm going to have minus j 100 divided by 1 plus j, which is from here, this j 400 plus 400, multiplied by 10 plus j4. So if I do the calculation, I'm going to have h of j omega as 6.565 with an angle of minus 156 degrees. So you have to do the calculation and you have to describe your answer in its polar form. Then this number needs to be multiplied by x, which is 2 with an angle of 0. So basically you have to add the angle. Because the angle here is 0, your final angle is going to be the same as the angle of h of j omega, and that's equal to minus 156, and you have to multiply the magnitude, so you're going to have 13.13 for the magnitude. So this is going to be your output phasor. Now that we know the output phasor is equal to 13.13 with an angle of minus 156, it means that our steady state time domain response is equal to 13.13 cosine of 400t minus 156. So here you can see how we can use h of s so directly to find our steady state output to a sinusoidal input. Basically what we are doing here is AC steady state analysis with variable frequency. So the only thing that varies here is our frequency. So this is what we call as AC steady state analysis. Now this can help us to think about filtering property. What is filtering property? So what is happening here is that the h of j omega is determines what is going to be the magnitude and what is going to be the phase angle. So when you're multiplying, let me continue on another slide. So when you're looking for your steady state answer, the phasor of your steady state response, you have to multiply your h of j omega by the phasor of your input. And it means that you have to multiply the magnitude of h at j omega by the magnitude of your input, and the angle is going to be the angle of h of j omega plus the angle of x. Now, if I want to describe my answer in time domain, it's going to be h of the magnitude of h at j omega multiplied by the magnitude of x cosine of omega t plus the angle of h at j omega plus the angle of x. So I know that my output to a sinusoidal input is always sinusoidal. The frequency is always the same. The only thing that will change when this input signal goes through the circuit is the magnitude and frequency. So the original magnitude of my input will be multiplied by this h at j omega, and the angle of my input, which is and the angle of x, will be added to the angle of h at j omega. So basically, I have the same input, but the magnitude is multiplied by the magnitude of h at j omega, and an angle equal to the angle of h at j omega is added to my input angle. So here you can see the filtering property. So it means that if I change my frequency, then h at j omega will change, and it can have different magnitude and angle. So it is important to know how everything changes if I change my frequency from 0 to infinity. And that's what we call as frequency response plot of the system. So in frequency response plot, we can focus on the magnitude of h at j omega with respect to frequency. So we want to see how this magnitude is changing if I change my frequency from 0 to infinity. We can also focus on the angle of h at j omega while we are changing our frequency from 0 to infinity. So what we have here is frequency response plot. I want you to notice that in our entire analysis, we have not only assumed sinusoidal input, but we are saying that let us look at this only in a steady state situation. So we will wait for the time to be really, really large, and then we are going to look at our response. And therefore, we will plot the response not as a function of time anymore, but rather we are going to plot the response as a function of frequency that you can see here.